Hello, everyone. Thank you for joining us today for this Consensus Program webinar on waste plastics gasification with carbon capture. Today, we will be presenting the results of a study that we carried out with the help of Battelle. This study was conceived in 2020. It was part of our FY21 work plan and was completed in December of last year. And so we are finally able to present it to the public and very excited to do so. For those of you who may not be familiar with the Consensus Program is a cooperative agreement with USEA and the US Department of Energy's Office of Fossil Energy and Carbon Management that seeks to educate the public, policymakers, industry, and other stakeholders and build a consensus on the benefits of and requirements for carbon capture, utilization, sequestration, and other carbon management technologies such as hydrogen production, rare earth elements, critical minerals, and the like. We do this through a series of activities such as briefings and webinars like today's. We have workshops, which during COVID times have obviously been virtual and will soon be hosting in-person workshops as well. We put out a series of reports and studies throughout the year, such as what we'll be discussing today. And then we also have a monthly news clips that we email list that we put out to our industry stakeholders. If you'd like to subscribe to our mailing list, please email my colleague Michelle Littlefield at mlittlefield@usea.org. Just a quick disclaimer about the webinar today and the study with which we'll be discussing. And just quick instructions, ground rules, logistical note. This webinar is being recorded. It will be posted on the event page on our website, and we just kindly request that you give us a few days to do so. We will also post a PDF of the presentation there as well, and that's where you'll be able to find this study after the webinar. Please enter any questions, comments that you may have in the Q&A box. We will address these at the end. Just a quick note on the agenda for today. Sheila Hollis, Acting Executive Director of USEA, will discuss USEA in just a moment here. Mike Moore, who's a Program Director at USEA, this study was sort of his brainchild. He's the one who proposed it, so he'll go through kind of his thought process on that. And then we'll have the Battelle team present the results of their study and how they went about it. And to reiterate, we will hold Q&A until the end. So with that, I'm going to pass it off to Sheila Hollis, Acting Executive Director at the U.S. Energy Association.
Thank you so much, Alex, and welcome everyone. On behalf of the United States Energy Association, we are delighted and honored to be participating and encouraging and supporting this program. A few seconds about what USEA is and does. USEA is nearly 100 years old. It has been dedicated to the sharing of information, the encouragement of study and analysis, and accessibility to the public and to the specialists who are particularly interested in energy and environmental issues. Been around since 1924. We also have another set of programs related to all of our work internationally. We've worked all over the world, 104 countries throughout the world, to improve the energy situation, to provide energy guidance and assistance, all with the hand in hand with the U.S. government, that is DOE and Department of State and USAID in particular. So I'm honored to be here and extremely delighted to have this outstanding, intellectually gifted and dedicated group of people who are looking to solve one of the major issues of our problem of our time today, which is to deal with CO2 emissions, and in a way which it makes sense and which encourages in energy development and utilization, not only in this country, but throughout the world. Thank you so much.
Sheila, thank you. And it's quite an honor to be part of USEA with you and the rest of the team to be able to explore these areas and do the work that we've been able to do. And it's always fascinating what our other departments are also up to as well. As Alex had mentioned, I had a hand in putting the idea together. It was kind of a background experiences, other conversations, people I know in different parts. And the issue of plastics is huge. I don't have to talk much about that. It's on everybody's radar screen. And plastics are very diverse, and it's an all-encompassing word with lots of issues. And on the other side of the equation, we have energy opportunities. And of course, what's happened in the last 30 days has changed the energy resource balance considerably. So a different consideration today that wasn't there when this idea was put together to be explored. Brandon will take you into it, but they had to look into a handful of different areas of expertise and markets and players that would not normally interact to pull the information out, to connect the dots and pull this study together. Any one of the slides that they're going to present to you today, I would assure you could do a whole program just around the one slide. Incredibly deep information in this that they had to go through. But the idea that plastics as a waste becoming more of a resource is maybe more true now than ever before because of what we've seen happen in the energy resource space. But there's a huge value proposition for its use as a feedstock for synfuels or syngas, but also to create BTU content that would be otherwise disposed of in a landfill, for example. And then you got the issue of landfills that are rapidly filling up, and of course, plastics are one of the major contributors to the rapid filling up of the landfill space, which is getting tougher and endured to put together. Put all that together, and you do this gasification process, and you end up with CO2 that you can either utilize, maybe because of the fertilizer world condition now, again, in the past 30 days, you use the CO2 for urea creation, for fertilizer, instead of for geologic storage. And either way, it's removed from the atmosphere. At any rate, lots of moving pieces, lots of new considerations, and Battelle and the folks have done a phenomenal job squishing all this stuff into this 1 hour presentation, which is probably going to fill everybody's slate with new ideas and things to work on. With that, Brandon, I'm going to turn this over to you, and thank you and Krista, your lead, and everybody else with Priya and Dipti. I really appreciate the work you got into it, and I made this comment to them earlier. I'm pretty sure that what it took to put it all together was far more than what we originally had set out to in the package. In other words, you've got a lot of extra time working this together I'll give you verbal credit for it and go from there. And thank you. So Brandon.
Well, thanks, Mike. Thanks, Alex. Thanks, Sheila. Just on behalf of Battelle, I'd like to thank you all for allowing us to kind of conduct this work as well as present this webinar. I think it's really important. As you mentioned, each of these different technologies are existing and so to go through all the information that's in there is quite a bit of digging that the team had to do, and then also kind of concatenated it into a single system. So I appreciate that. You'll see this webinar really only covers, it kind of brushes the surface of what's in the report, and the report only kind of brushes the surface of what's in this kind of potential technology. So with that, speaking of technology, let's see if I can share my screen here. Perfect. You guys seeing the presentation mode? There we go. How's that? And I'd also like to thank all the viewers that are watching this. So this, I'll kick off here. It's been funded. This is our kind of standard thing. It's been funded under the cooperative agreement that we've discussed earlier with Alex. So today, I'm going to take you through the introduction. Here's an overview of what we're going to talk about. I'm going to be trying to set the stage for what the problem is and what the potential solution is. I'm going to hand off to Priya. She's going to walk through in a bit more detail on the co-gasification as a potential solution and the carbon capture utilization and sequestration or storage, depends on how you want to term it. And then Deepti is going to walk us through the state of the art and the future steps. And then, as Alex mentioned, we'll handle questions at the end. So today we're going to discuss a novel combination, as I mentioned, of existing and kind of existing and proven technologies to address a plastics waste problem. You know, anecdotally, I think a lot of folks will kind of think that recycling's gained a major foothold in the United States, and we've made progress, but basically we're still only recycle about 8.7% of the plastics. You combine that with a shift from coal to natural gas for power production, leaves a whole lot of coal resources still in the ground within our borders. So if we can combine those resources with a process called co-gasification, we can create a product called syngas. Now, syngas, as Mike mentioned, it's a molecular building block to be used to build up all sorts of things like liquid fuels and plastics. You can kind of go back in a circular process to rebuild plastics. And if we're able to couple this with carbon capture and storage or utilization, depending on how you want to work it, this will allow us to kind of move towards a more environmentally friendly way of handling plastics recycling. So as you can kind of see here, since the 60s, this is ballooned quite significantly. There's a very large portion of this in our current domain that basically is plastics packaging. That's been really growing. If you've ordered anything recently, you'll know there's plastics packaging everywhere. A whole lot of it gets landfilled. Now, there has been some progress with combustion and energy recovery and recycling over the years, but still the major portion is still landfilled. And we have a theory behind that. Some of it is around just the thought process. And basically, we kind of feel like plastic shouldn't be considered a waste. As if it's discarded, it really needs to be considered a valuable resource for kind of recycling processes. So we're on a journey here. We use plastics on a daily basis, from kind of the trivial general convenience items to life-saving devices. We, however, kind of need to change our perspective. If we can change the paradigm from the plastics are waste to plastics are valuable resources, it has a major impact on kind of how people behave. Have you ever seen the trash can that says landfill and recycle? It's that kind of mentality. This is also kind of a positive spin on it, the carrot side of things, where there is value in there, and from a BTU standpoint, from reconfiguring it into some other product that is more valuable than sitting in a landfill. So we are currently on the journey, as I mentioned. The left side of this particular image shows a linear economy. So we recycle absolutely none of it. That's one side of the paradigm. The other side is a circular economy, where everything's recycled, and that's kind of our ultimate goal. Where we're at, if we're in the middle, the reuse economy. These things do not take place overnight, and they do not take place in kind of a single step. These are progressive. And as I mentioned before, we're only at 8.7% recycling. So we're in the reuse economy. 8.7% in the United States gets recycled. So that's where we are today. We have quite a ways to go. Part of what Priya and Deepti are going to talk about is a potential solution for this. So let's talk a little bit about current recycling methods. Primary recycling is essentially reintroduction of scrap to the extrusion cycle. It gets used all the time, but it just needs almost really clean scrap to put back in the extruder. Otherwise, it messes up the system. Secondary recycling is mechanical recycling, and it's limited to single polymer plastics. So it's energy intensive and also takes a lot of sorting to handle those. We're going to talk a lot about tertiary recycling today, and that is basically converting plastics into materials, into liquids and gases, and that could be converted into other materials. It's more complicated, but it can create higher value products. And then, of course, quaternary recycling is recovery of energy via incineration. There are potential emissions and toxicity issues if this isn't carried out correctly. This, however, is taken foot in Europe, and quite a bit of the European countries use some form of this for their plastics recycling. As mentioned, in other areas of the world, people handle plastics differently. This red box here shows basically all the countries within the EU that landfill less than 10% of their plastics, and you can kind of see most of it's under energy recovery. In addition, they've developed in the EU specifically has developed different methods for reduction in single-use plastics, and it's a multi-pronged approach. You know, they basically they've got awareness campaigns they've developed. They've implemented design requirements to lower plastic content in products. They've passed legislation to reduce waste reduction, and basically, and sometimes they also require the use of warning labels on some of their products. Kind of like that trash can example I was talking about, where, you know, do I really want to do something with it? Do I want to buy this product or that product, depending on plastics content? So with that, I'm going to turn it over to Priya to walk us through co-gasification as a potential solution.
Are you able to view my screen now?
Yes.
Okay. Thank you, Brandon. I should be talking about how the study that evaluated co-gasification of plastics as a potential solution to manage this increasing amounts of plastic waste while creating a value proposition for the same. Co-gasification is a tertiary or a chemical recycling treatment technology, like Brandon mentioned, that provides the benefits of gasification while offering additional flexibility and synergy. Now, gasification is a prominent and very well-established technology. It's been used to convert coal and even plastics, essentially pure feedstock, into valuable gas and liquid products. And especially for plastics, their high calorific value and low moisture is very desirable. But the gasification of plastics has been faced with multifold operational problems that are associated with the choking of equipment because of the softness of plastics and their stickiness at high temperatures and black particle formation, etc. So co-gasification is an emerging technology that has been demonstrated to control these operational problems, and by blending these plastics with other carbonaceous feedstock. And there's also potential to control the product gas specification. So it is very versatile in that way. Now, plastic waste can generally be added to this coal and biomass gasification processes without any major changes to it. And it's been studied for the past 2 decades at the laboratory and pilot scales. So it is currently at the pilot scale technology readiness level, and it still needs to be commercialized. But here are the main operations that are involved in co-gasification, similar to the gasification process itself. There is an initial processing to dry the feedstock. So the mixed feedstock, there is some amount of moisture control that needs to happen. And after this drying, we then feed it into the pyrolysis unit. And this is followed by high temperature oxidation and reduction. So oxidation in the presence of oxygen and then reduction in its absence to give the final product, which is synthesis gas or syngas. There is also some tar and ash formation. These are non-desirable byproducts. So our focus here would be the product synthesis gas. So the syngas is essentially a fuel, like Brandon mentioned. It consists of hydrogen, carbon monoxide, and carbon dioxide. The other byproducts will determine the economy of the process, so because they're related to the cleanup operations, but I will touch upon them later. Syngas, like I said, is the main product gas. And so we are looking at it because co-gasification, the syngas that is produced from co-gasification can be a very viable, greener alternative source for this gas. And if you can see here, this shows the different applications of syngas. It is a fundamental building block for a myriad of operations, including energy production, fuels to industrial and chemical applications. So it is a building block and a very critical intermediate material. About half the syngas that is produced goes into ammonia synthesis for fertilizer production. Some of these applications require the syngas to be that can be used directly, whereas some require post-processing or conditioning for use if they're specialty applications. But because of all these uses, especially because of the demand from the chemical industry, we see that the market, both globally and domestically, for syngas has exhibited strong growth and is still continuing on a positive outlook from various market predictions. And the shift towards hydrogen economy is also expected to boost the demand for hydrogen production that can be complemented by plastics gasification. Co-gasification, like I said, it provides the versatility of gasification, and there are potential synergies that have been extensively studied with different feedstock combinations. Our focus here in the study is the plastics bubble. So we look at mixed plastic waste, the combination of plastic with coal in particular. The combination of biomass and plastic is representative of municipal solid waste. But this is essentially going to be the focus of the study and the talk as well. Okay, so the performance of these co-gasification systems and the quality of this product syngas are very dependent, and they're driven by these critical process parameter conditions, which are listed in the blue circle. So we have definitely the composition of the feedstock mixture itself. But apart from that, the conditions of the gasification, like the temperature, the operating temperature, the equivalence ratio, and the choice of the equipment and materials, like the gasifier type, the medium that is used for the gasification, the catalysts that are being used, all these things play a very important role to drive the product yield and the performance. And some key metrics that are used to determine the efficiency of this gasification performance are shown on the gray box to the right, which includes the composition of the product gas, the proportion of hydrogen and carbon monoxide and carbon dioxide in the product syngas, the yield, the gas yield, the heating value of this product gas, and the tar content, like I said. Now, because tar is an undesirable byproduct, we would like to have an operation that will minimize the tar content to help improve the economics and the cleanup associated with the product. Now, an important process consideration is the choice of the gasifier itself, which is the type of the reactor that is going to be used. And there are three types of gasifiers: the fixed bed gasifier, the fluidized bed gasifier, and the entrained flow gasifier. Co-gasification has been demonstrated sufficiently in all these three types of gasifiers, but they have different uses typically depending on their suitability. For example, the fixed bed gasifier is the simplest in design, so it's primarily used for small scale applications. Plastics gasification widely uses the fluidized bed type of gasifier for large-scale plastic gasification operations. And if the feedstock has varying moisture content because of the multiple sources possibly, then entrained flow gasifiers would be really suitable for such large-scale applications. So I mentioned the flexibility that co-gasification offers because of the different feedstock blends. And this is very critical, for example, in situations of limited supply or seasonality that we want to still address and get the product syngas to utilize. But at the same time, the proportion of the feedstock mixture and its composition is very crucial and it impacts the product yield, the composition, the tar content that is generated. So it essentially is essentially one of the critical parameters that we can control the output specification itself. And an example study shows, if you look to the graph on the left, it shows different proportions of coal and biomass and plastics indicated in C, B, and P, and the evaluation at specific operating conditions to see what the impact of these different blends are on the gas composition itself. And for example, it was seen that the ternary mixture, which had 80% of coal, 10% biomass, 10% plastics, gave the highest amount of hydrogen. And the more the hydrogen, the more its value in fuel-related operations because it has a higher heating value. Similarly, if we look at the tar content, the graph to the right shows, for example, that pure plastics will have an increased tar content that can be controlled by the addition of biomass and coal, for example, in the study. So this is a summary of the key findings from different research activities over the past 2 decades that I mentioned. In general, for a desirable syngas, if we would require a high heating value, that corresponds to us requiring a higher hydrogen content in the product gas. Generally, low yield of char and low tar content is desirable. And at the same time, of course, higher gas yield is what we will strive to achieve as part of this process. There is not one unique optimal process condition, so to speak, because it typically varies depending on what the application is of that products and gas, because different applications, like I said, require different specifications. So, and at the same time, the feed, the hydrogen to carbon ratio in the feed, like plastics and lignite, are also very important to realize the synergy in this co-gasification process. Now, the second component towards achieving these reduced environmental impacts while managing plastic waste is the CCUS piece, or the carbon capture, utilization, and sequestration piece. Commercial plastics co-gasification would release significant amounts of carbon dioxide, and CCUS is one very viable way to realize both the economic benefit and the environmental benefit of managing plastics in this fashion. Because coupling a CCUS system with a co-gasification facility will enable the removal of the carbon dioxide that is being produced, and we can redirect it to either a process that will utilize this carbon dioxide to produce industrial or consumer products of interest, or we can sequester it safely in the permanent geologic storage, so we can put it away safely deep underground as part of the storage operations. So there are 3 components that are involved in CCUS. The carbon capture, which is the critical capturing of the carbon dioxide that's being emitted. We have different methods of capture that are well established. And there are a number of these technologies that can also be compatible with the gasifier use. For example, existing solvent-based technologies are compatible and they're well established globally for gasifier use. The second component is the transport. We have, again, multiple options to transport this carbon dioxide to the place of use. It could, if it is for storage, then again, we have multiple options in the subsurface. So deep underground, there are different types of formations and rocks where we can put away this carbon dioxide safely, and it has been demonstrated. So this aspect of capture and geologic storage has been well established, and commercial implementation spans multiple decades across the globe. In the United States, we have sufficient estimated potential for storing carbon dioxide geologically in these different formations underground. It could be in saline formations or depleted oil and gas reservoirs or unminable coal seams. And it also includes existing regulatory infrastructure that can be leveraged, and you can store the carbon dioxide from plastics co-gasification as well. There are existing financial incentives like the 45Q tax credit programs that can also help offset project costs while sequestering this carbon dioxide. Apart from the storage, like I mentioned, the carbon dioxide can also be utilized into new products. And there are numerous established and emerging technologies for this, where we are trying to find value in the carbon dioxide that is being captured. Carbon dioxide can be converted to useful products, varying from fuels to organic to inorganic chemicals, concrete, working fluids, and research currently is focusing on improving the efficiency and the economics of these processes. But it is currently one of the important topics with respect to utilization of carbon dioxide. Thank you. I shall hand it over to Deepti to, since she will take us through the state of the art and the future steps.
Can you see my screen? Can you hear me?
Yes, we can hear you and see your screen.
Okay, great. Thank you so much. Sorry about the delay. Thank you, Priya. Thank you for going over the co-gasification and CCUS piece. I am going to be summarizing what Brandon and Priya talked about and go over the current state of the art and our assessment of what the future steps may be to move this concept forward. So as Brandon talked about, we have an abundance of plastic waste and only 8.7% is being recycled. So, and there is a rich coal reserve in United States that we can capitalize on. If you can actually see the graph on the bottom, Wyoming, West Virginia, and Pennsylvania, these are all states that produce a lot of coal. And we can, capitalize on the location geography of these coal-rich reserves with plastic waste diverted from the landfills as a low-hanging fruit and use it for co-gasification, resulting in a versatile product, syngas. As Priya talked about, the syngas market is only increasing and there are so many applications to syngas. So there is, this is a very promising technology. And the last step being coupling the co-gasification with the CCUS system to reduce the greenhouse gas emission. Now, this sounds great, and what we've seen is there are some technical challenges to achieve this. And I'm just going to go over some of those technical and non-technical challenges. So some of the technical challenges are about, your pre-processing and upstream processing in co-gasification and then the downstream processing. So in the upstream processing, feedstock preparation is very important. What we see is a lot of these facilities have a lot of feedstock outages due to different mixed scrap plastic waste and the sizes and shapes of this mixed feedstock. There are different kinds of moisture levels. So all of these, lead to clogging of the system. So there is a need for understanding and scaling up the pre-processing stage of co-gasification of mixed feedstock. The other important aspect of the technical challenge is the syngas cleanup. To be able to utilize the syngas, it's very important to make sure we have the tar removed, the alkali removed, and all the particulate matter that's there in syngas. And these have been demonstrated very successfully in the lab scale. However, we haven't been able to, commercially move it. So scaling up of that is also very crucial. Brandon touched about some of the non-technical challenges that we've seen. Landfills in the US are a go-to waste management solution. US is a large country, it has a lot of land. So, the cost for landfilling is cheaper than in most countries. And we've also seen the current policies are not quite favorable to recycling plastics because our plastics that are recycled is about 8.7%. And I believe about 75 to 80% is completely just wasted. So, and this sort of behavior is also shown in our social awareness. people don't consider plastic as a resource. They look at it as a waste. So there needs to be a shift in how we approach this. I do want to say that in spite of all of this, we have seen some good operational facilities that are functional in globally for co-gasification, and two of them being in United States. One of the longest running ones is in Japan. Japan being a really small country, you know, they've had to be very stringent about recycling and about plastic waste. And so they've been, this JGC group has been operational since 2003. They've been using the syngas, that's a product of co-gasification, to manufacture chemicals like ammonia. And Canada, Enercom in Canada has been operational since 2017. However, it started off as a pilot scale, and I believe in 2003, and scaled up to commercial operations in 2017, manufacturing ethanol. Sierra Energy and Fulcrum are the two promising ones in the United States, and Sierra Energy is now in a pilot scale and looking to move towards the commercial, advancing its technology, trying to, you know, do collaborations with public and private sector to improve its technology and scale it up. There's a lot of research in this field globally, and specifically the Department of Energy and National Energy Technology Laboratory in the US is driving a lot of this research. And they are focusing on modular gasifier designs, you know, process efficiencies, trying to understand the use of local feedstock, how to use that to ensure that we can try and reduce costs. And there are other studies specifically on the mixed feedstock blend. How do you use plastic, biomass, and coal together to successfully generate energy and scale that up, try to look at how to move into a commercial market space. One of the things that we found in our study, you know, when regarding what Brandon mentioned, you know, the EU and there are other countries that have moved far along in moving towards circular plastic economy. We've observed a few things that worked for those countries. So we thought it'd be beneficial to put that together and you know, something to think about. And this slide talks about some of those observations. Our current landfill policies, you know, try to look at landfill taxes, try to figure out the fees, restructuring fees, tipping fees. Then an awareness at a city and municipality level on plastic waste management, about plastic recycling technologies. For example, I wanted to bring up an item that in Japan, the responsibility and the onus of segregating plastic waste is on the citizen. It doesn't get collected unless it's segregated there by the citizens. So things like that can help at all levels, at public, city, and municipality level. Then there can be state and federal initiatives that just promote the use of recycling technologies and specifically chemical recycling technologies to, you know, harvest syngas. So things like that. And another example would be to promote the use of government, coal, and plastic industry consortiums to look and evaluate at the use of recyclates instead of using virgin plastic in these industries. Another example would be Netherlands, which is the furthest along in a circular plastic economy. When you look at all the countries, they have a goal of reducing plastic waste, I believe, by 2025, which is not too far away. And they have a collaboration, industry and the government, looking at how they are going to be replacing the virgin plastic with recyclates in their manufacturing. There are also other, you know, resources globally and in-house. You know, American Plastic Council has an American Chemistry Council. These are all resources that are available. They look at technology collaboration between public and private sectors and try to disseminate information and advancement of syngas. For example, the Global Council of Syngas, Global Syngas Tech Council. So there are a lot of resources that are available that have a lot more information on what are all the kinds of technology developments and advancements that are possible with plastic waste management. For more information, you can definitely go to a report. This is just a little, sprinkling of information we found during our study. So to wrap it all up, plastic waste is not a waste. It's a revenue resource. We need a shift in mindset to look at it that way and utilize plastic waste to, produce syngas via co-gasification. There is a certain value proposition in utilizing coal, the rich reserves that we have within United States, and combined with plastic waste using co-gasification. And as Priya talked about, there is a huge amount of storage potential for carbon dioxide within the subsurface in United States. And not just to store it, we could even utilize it. There are established novel upcoming technologies where we can divert the carbon dioxide that's produced as part of co-gasification and reduce our environmental impacts. And then finally, to address the gaps in what we've found in social behavior and policy and other aspects, technological innovation aspects. So that is all from us. And thank you all for your valuable time. And I'm going to hand it over to Alex for questions.
Great. Thank you so much, Deepti, and thank you, Priya and Brandon, for a really, really interesting study. Great presentation. Very much appreciate the great work that you all have done. I remember growing up having it drilled into my head that we need to always be recycling, and so, I feel like we go through a lot of effort to recycle, and then to find out that, less than 10% of the plastics in this nation are recycled. It was kind of a shock to my system and in my sense of being a quote unquote environmentalist. And I think everyone's heard of, our plastic waste issues and, getting rid of single-use plastic bags, getting rid of plastic straws and this and that. And, but it seems like a lot of what we've been doing surrounding the plastic waste problem hasn't been effective. So we need to kind of rethink the problem and rethink the solutions. And so I think the work that you all have done is incredibly valuable. So thank you for that. We will take questions at this time. So if anyone in the audience has any questions, please feel free to type them into the Q&A box or the chat box. We have a great question that came in from another Alex. Are there any contaminants in plastic, such as chlorine from PVC, that bring new technical challenges not common in coal gasification? If so, how is the treatment step being modified to be able to handle these species?
Yeah, I can start on that one. Yes, there are definitely post-processing or downstream processing that will get added on because of the presence of plastics in the feedstock. So there are many operations in terms of the cleanup that would be similar to what we would do for coal gasification in terms of nitrogen removal, alkali removal, particulate matter removal, things like that. But because of the presence of chlorine and halogen compounds, there would be additional steps that would complicate this conditioning and cleanup. Because you want to avoid catalyst poisoning, you want to avoid emissions, you want to avoid corrosion issues. So these would definitely be added on. So you're right.
Great, thank you so much, Priya. Another question, I think this is probably for Deepti. You mentioned that the Netherlands is the leader, kind of the world leader in plastics recycling and whatnot. How far ahead are they? What percentage of plastics are they able to recycle or reuse? Kind of what are we working with here on the world stage?
The specific number what comes to mind is about 85% to 90%. But the point to note is a lot of these European countries, they have not much land. So landfilling is practically, less than 10%. If you saw that graph that Brandon shared, they have a lot of waste to energy recovery processes, and they use that for heating and sometimes for electricity. Netherlands, as far as I recall, I believe it's about 85 to 90%. And their goal is to get to, 2025, which is quite an ambitious goal. Remove plastic waste, to have it all in the system.
Got it. Thank you for that. And I noticed that Sheila has come back on camera, so I'm assuming that you may have a question, Sheila. So the floor is yours.
How expensive is this going to be? I mean, how can this be budgeted in for the future to really pursue this program to the max? And is there enthusiasm throughout government for this program throughout the governmental entities that are interested, that really backs this enthusiastically, because it is such a great insight-filled presentation. It opens up so many possibilities for improvement, not just now, but forever with this technology. So just really interested in what you're hearing.
So when we did this study, we kind of necessarily excluded cost at this stage. This was more of an eye-opening kind of, let's put these things together and see if we can actually even, concatenate them and get some kind of process that works fundamentally. I think as we go through processes like this webinar and getting the paper out there and kind of getting some more folks involved in it, obviously we need to move from FOAC, first of a kind, down to nth of a kind in order to get that down that learning curve in order to kind of get any kind of economies of scale. So I mean, part of that has to do with what Deepti was talking about, is around there's some policy changes and there's also some economic drivers, just like we see in CCUS for other industries. It's a little bit of carrot, a little bit of stick, and then depending on that mix is kind of what dictates what we've seen in the EU and what we're seeing in the United States. So short answer, that's a long answer to your question. We don't have cost numbers just now. It's the first time we've kind of put this together and seen if from a technical perspective, this is something that would be potentially feasible. Sorry.
I just want to add one point to that, Brandon. Sheila, what we did see is we did see some examples of failed operational facilities, and a lot of them came down to finance. So there seems to be a high capital for sure, which sometimes is probably causing some failures. We don't know the dollar amount, but that was definitely, there were technical, operational aspects that caused the failure and financial. So.
Thank you so much.
Yeah, thank you both for those answers. Another question that came in, while I understand the amount of tar or ash will vary by feedstock composition, what's the typical range of waste versus syngas by weight?
I wouldn't be able to tell you off the top of my head with respect to weight, but we did see a good amount of variability, even when you consider like if it was 20% of plastics versus if it was 50% plastics in the feedstock mixture. We saw tar content varying from like I think it was gram per meter cube. So it would vary from 1 to 100 grams per meter cube with respect to the tar content. For very similar operating temperatures, it just depends on what sort of bed material was used. So all these were essentially lab studies, but it looks like there is definitely scope for optimization there with respect to the choice of different process considerations.
Thank you, Priya. Now, a comment that came in is that there are good markets for number 1 and number 2 plastics, and in states that have bottle bill and have material recovery plants that can recover plastics, unless more states get bottle bills and build more recovery plants at an expense, we cannot recover the plastics. And film plastics are of course a problem. Do any of you have any comments on in response to that?
I think it sounds absolutely reasonable and fits with kind of some of the municipal / government policies that would need to kind of be in place to make sure this stands on its own. And the film plastic's absolutely a problem.
Mm-hmm. Thank you, Brandon. Another question that came in: are there private entities that are currently interested in funding development work for biomass, MSW, plastic co-gasification?
Mike might be able to weigh in on that too. I don't want to pull him into this, but yeah, that's and Deepti, you can answer that question.
Private entities, I'm wondering if the question is more geared towards the US. There were private and public resources that when we were looking through our study, we found one that comes to mind. I don't know if it was multiple countries coming together to look at bioenergy aspects of exploring plastic waste. I believe it is called Task 33, and it's in our report. I don't have the full detail. But that would qualify as a private. I mean, it's not under a government. It's multiple countries coming together.
I don't on my side, I can't name a particular company coming in to do this. It's actually to package all this up takes a lot of different disciplines. And as an example, in West Texas, there was a project that was going to be one of the early CCUS projects, and they were going to make urea. They had CO2 for the EOR markets and storage. They would produce electricity, do a number of different things. And we were I was part of, we were close to the entity. What they ran into is that each area of value for the project was stovepiped in terms of the engineering firms, the construction companies, the design engineers, and the whole area was in a way that you had to work almost independently with these different disciplines and market sectors, then try to package it all together into a financeable, manageable package. And they all had different terms and conditions and risk factors that weren't aligned. And my guess is that it would take any firm that would do this, somebody that has done some kind of at-scale project where there's a number of different moving pieces that have different market values, have different funding programs, have different risk applications that they're comfortable dealing with. Because there's a lot of moving pieces here to bring all that under one roof like that. But that leads me from an energy standpoint. The mixed waste plastics, I mean, there's probably no average aggregate. It's going to be different geographically, seasonally. There'll be a lot of factors as to what kind of plastics are ending up in the landfills or headed that direction. But if I were to look at, say, the BTU content of this aggregate in relation to coal or natural gas or to hydrogen, how much energy is actually on a weight to weight basis does waste plastics have to everything else?
Priya, do we have any information on that we can share off the cuff?
No, probably not.
Yeah,
We
I
can look
don't
more into
believe
that.
we have.
Yeah.
And I guess on a similar note, another question that came in, and I'm not sure if we have an answer for this either, but what kind of technological advances would be needed to allow for 100% plastic gasification?
I can start that off. I think just sort of leading off of Mike's point, where the waste that we call plastic is so mixed and it varies geographically, seasonally. We do have studies that focus on specific components of plastics and not looking at mixed plastic, whereas some look at mixed plastic waste. The issue that we have seen, like I mentioned, all these operational problems is what needs to be addressed. We can go two ways. One is the co-gasification route, which is what the charter of this study was. But there is also the opportunity to work some more on the catalyst side of things. So we can use catalysts to help overcome some of the problems and retain the desirable qualities of plastics for us to process them more efficiently. So that's something that can be looked at.
Thank you, Priya. And we've had a generous offer from one of our audience members, Tony Licata, who has the data on heat value of plastics that he can provide later if anyone would like that info. So if that is of interest, please get in contact and we can make that connection. Segueing, there's got a related question. Given the heterogeneous nature and different blends ratio of the feedstocks like coal, biomass, mixed plastics, are there any currently available technologies that can provide accurate and on-time component analysis info for the gasification feedstock?
I don't think we've run across any. It's a great point, and it's the piece that would allow you to run your gasifier in a kind of a normal operational mode that's able to kind of handle any influx. You basically add more coal or biomass or whatever, depending on the BTU content and types of plastic you're feeding. Did you all run across in your other areas that you looked at? Did you run across any technology? I do not know of any.
No, and I just wanted to say, Sierra Energy, the project that's a pilot scale co-gasification project that's trying to scale to a commercial space, is looking at all of that, trying to see how to optimize that.
Thank you for that. That's helpful. And now one last question, and I think we may have touched on some of this, but could probably use a little bit more clarification. Besides the CO2, were process emissions also evaluated for other air pollutants such as particulate matter, VOCs, and HAPs that would also need to be controlled?
Yes, definitely. We focused more on the carbon dioxide aspect of it, but there's definitely emission control with respect to all these other emissions as well that needs to be controlled. The one advantage is it can be controlled much more efficiently than incineration, which we did see. So that's the benefit of going the co-gasification route instead of incinerating the plastic. But we did not look into addressing or remediating any of these emissions specifically.
And as part of syngas, I just wanted to add, as part of syngas cleanup, those are aspects that are dealt into, like, yes, for example, sulfur compounds, you need to remove all of that for emission control. So.
Thank you for that. It looks like we have about 2 minutes, 1 to 2 minutes left here. So just want to give anyone the opportunity to enter any last minute questions or comments into the chat. Mike, do you have any final thoughts that you'd like to share?
Just that great work opens up some new lines of thinking of some of the things you put together in your work there. If you took any one of these moving pieces, which one would you consider to be the most critical one to further develop? And I know there's a lot there, and each would have its own priorities inside their own market sectors. But if you were tasked with saying this area needs to be developed further for this whole idea to work, is there one particular area that you would recommend that a deeper dive would be done on?
I think another way to answer your question would be, if it were to us, maybe we'd look at, all right, let's pick one state where we have coal gasification ongoing. Can we look at the process more closely? Is there any CCUS system close by? Let's look at the infrastructure that's existing. Can we put all these pieces together? What we're talking, can we walk that talk? That's how I would probably, the first step.
Yeah, it's a good point because it goes back to Mike, you were talking about project finance and then couple that with like early stage tech development. So I've got project finance issues already with the 4 legs, and then basically I got a tech development. Yeah, because I think we, Deep, Priya and I would probably all disagree and agree at the same things. I think that the gasification technology, I think while it's established, handling varied to the one question's point, handling varied mixtures. I don't know if they're pre-sorting stuff now, but handling varied mixtures of things as an operation is difficult for your facility. So I think that's one that's massive. Getting more folks to kind of not landfill it is another piece of it. I don't know that I could pick my favorite today.
All right, I appreciate that.
We're
Priya?
up there.
Yeah, no, I agree with both Brandon and Deepti somehow. The first thing is with respect to the actual implementation of this co-gasification. We need to see that synergy that they've seen in the lab. So some more scaling up, we need to move the scale up and see if it can be done on a larger scale. And if it is done, then we can, the next step would be then looking at all the other infrastructure that we can leverage, because like we said, CCUS is established, we have plants that can capture. So all these technologies are there. It's just a matter of putting them together at that point. That's where the finance would sort of drive the bigger project. So I think move it like that probably would be more meaningful.
Very helpful.
Great, thank you. We are over time now. One last question that came in was how to get in contact with you all for further information. So please just feel free to email me at akrowka@usea.org. That's akrowka@usea.org, and I will pass on your information and your questions to the Battelle team. Sheila, I see that you've come back on camera. If you have some closing thoughts you'd like to share.
Just thank you to the Battelle team, and thank you for all those who are listening in today. Incredibly interesting, fascinating, and replete with opportunity. So thank you so much.
Yes, couldn't agree more. Thank you everyone for attending today. Thank you to the Battelle team. Again, just really great work, and really appreciate you guys taking the time to share this with us.
Thank you all.
Thank you all.